Okay, this is the first section in chapter 1. We're going to break this up into two different lectures. So the first one will be section 1.1a. So we'll start by talking about real numbers, which if you think of a number line, every point on that number line is a real number. And every real number is a point on that number line. Okay, so we'll call that a one-to-one correspondence. But let's talk about how we make that number line up. So we start with the natural numbers, which are just our counting numbers, 1, 2, 3, 4, and you can see those there. So the ellipsis, those dots mean 5, 6, 7, 8. It just keeps continuing in that pattern. Okay, so that's natural numbers. Okay, and then integers, we include 0 and all the negatives. Okay, so when we talk about integers, we're looking at the natural numbers with the negatives and 0. Okay, no decimals on any of these. So if we drew our number line, we would have the integers would be our marks like 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, and 0. Okay, so that would be integers. Okay. Now let's talk about rational numbers. Rational numbers are ratios. Okay, of integers. So if you take an integer divided by an integer, you get a rational number. So m and n here are integers, and then r is the rational number. Okay, so we can, anytime we can divide two integers, we have a rational number. Now the one thing we can't do is we can't divide by 0. Okay, so anytime you're dividing by 0, like 3 over 0 or 0 over 0, then those are undefined. So those are not rational numbers. Okay, so we could have like 1/2 or minus 3/7. 46. So any integer we can write as a rational number. 46 over 1. 0.17 is 17/100, so we can write that as a rational number. So the characteristic of rational numbers is that the decimal stops or repeats. Okay. Then we talk about irrational numbers. Now we get to irrational numbers. We're talking about decimals that don't stop or repeat. Like if you think of square roots that aren't even square roots, like square root of 2 or square root of 3 or square root of 5, those are irrational numbers. The decimals just keep going. Okay, so they don't stop or repeat. Okay, pi is another one. Okay? So those are irrational numbers. So here's some other examples of irrational numbers. We have square root of 3, square root of 5, cube root of 2, pi. Anything involving an irrational number in adding, subtracting, multiplying, dividing also results in getting an irrational number. So we talk about irrational numbers. We'll talk about by example. Okay. Now if we put those together, okay, this is how we get our real number system. So on the one side here, we have our natural numbers, 1, 2, 3, 4. And then the integers include those. So we have that bigger purple box, includes the natural numbers, but it also includes the negatives and zeros. That's how we get our integers. And then if we take ratios of those integers, we get rational numbers. So that's the bigger blue box here. So that's the one side we have the rational numbers. Okay. And that makes up part of the number line. The rest of the number line is filled in by those irrational numbers, where the decimals don't stop or don't repeat. So on the irrational side, decimals don't stop, don't repeat. On the rational side, the decimals either stop or have a repeating pattern. Okay. If you think of like 1/2, that's 0.5 and it stops. Okay. These decimals all stop. Something like 1/7 would be 0.142857 and it has a repeating pattern. 1/3 would be 0.333, etc. So here's some examples of rational numbers where the decimal stops, 0.5 for 1/2. Repeats, 0.6 repeating for 2/3. This would have a repeating pattern of 0.17, 157 over 495. 9/7 has a repeating pattern. Notice it's for 7 as a denominator, it has a 6-digit repeating pattern, then it just repeats. Okay. These irrational numbers like square root of 2, decimal just keeps going in a seemingly random fashion. There's no pattern there. Pi, that should be pi there. Pi equals 3.1415. Keeps going, right? So let's talk about the properties of real numbers. When you add two numbers, you can reverse the order of addition and you get the same number. So 2 plus 3 is equal to 3 plus 2. 5 plus 7 equals 7 plus 5, etc. We call that our commutative property. So there's our commutative property, real numbers. Okay. And here's kind of listing some of the properties. Looking at commutative property, you can switch the order and you get the same number. Okay. Same with multiplication. So we have commutative property for multiplication. So 3 times 5 equals 5 times 3. Associative property just extends those to 2 or more than 2. So if we're adding 3 numbers, we can switch the order of addition and we still get the same number. So 2 plus 4 plus 7 would be 6 plus 7. Or we could go to 2 plus 4 plus 7 and do the 4 plus 7 first, and that will give, either way we get 13. Okay, same with multiplication. So the associative property says we can take any 3 numbers, or more than 3, and multiply them in any order. Okay, so 3 times 7 is 21, times 5 is 105, or we could go 7 times 5 first and get 35, times 3 is 105. Okay. And then distributive property is a little bit different. So when you're adding or subtracting inside parentheses and you're multiplying on the outside, what you're going to do is multiply that a times the b, and then you're going to multiply the a times the c, okay, and then add. Okay, so 2 times 3 plus 5 is 2 times 3 plus 2 times 5. And then if it's afterwards, it's the same deal. So if the a is afterwards, you can do a times b plus a times c. So that's our distributive property. So here's an example of distributive property. 2 times x plus 3 is 2x plus 6, or 2 times x plus 2 times 3. Okay. If we have a 2 term times another 2 terms, we call these binomials because they have 2 terms. 1 term, 1 term, 1 term, 1 term. We can use FOIL. Okay, so what we're doing is distributing x twice on the a plus b, or distributing x on the a plus b, and then distributing y on the a plus b, right? Or we can do FOIL. Remember, FOIL would be first would be a times x, so that's there. Your outside would be a times y, which is there. Your inside would be b times x, which is there, and then your last is b times y. Okay, so there's the FOIL, not in the same order, but this would be your first, outside, inside, last. Okay, when we add or subtract numbers, if you're adding something to a number to get the same number, we call that additive identity. Okay, and we would add 0 to get the same number. So we say the identity element for addition is 0. Okay. When you're subtracting, basically you're just adding the opposite of a number. Okay, so if I'm saying a minus b, is I can say just add the opposite of b. So a minus b is a plus a negative b. Okay. This negative a we call the inverse. Okay, and what happens when you add the inverse, the additive inverse to a number, you get your identity element, which is 0. Okay, so that 0 here is your identity element. Okay, and you're trying to get to your identity element by adding the inverse there. Okay, so here's some properties of negatives. Negative 1 times a is negative a. Here's an example. Negative a is just positive a, so think of negative 1 times a negative 1 as positive 1. Okay. If I'm taking a negative times a positive, I get a negative. If I take a positive times a negative, I get a negative. Okay. If I multiply 2 negatives, I get a positive. And here we're distributing. Now what we're distributing there is a minus 1 times a plus b. You don't see the 1, but that's what that is. So it's minus 1 times a plus a minus 1 times b. So that's how we get minus a minus b. And then for this one, we have a minus b in parentheses, so it'll be minus 1 times a minus a minus 1 times b. So that's going to actually be a plus b here and a minus a. Okay, so be careful when you have negatives outside parentheses because it's going to change the sign of everything inside the parentheses. Okay, in this case, it changes to minus a and minus b. And in case 6, it changes it to minus a and plus b. Okay. When we multiply a number times something to get the same number, we call that our multiplicative identity. Okay, and that identity element is 1. Okay, so when you multiply a times 1, you get a. Okay, so anytime you multiply something times 1, you get the same number. So we call that our identity element for multiplication. Okay, the inverse, in this case, the multiplicative inverse, okay, is not going to be negative a, because if you multiply a times negative a, you get negative a squared, right? But if you multiply times 1 over a, you get to our identity element for multiplication. Okay, there should be a times there, but a times 1 over a is 1. Okay, so the multiplicative inverse is called the reciprocal. okay, which is 1 over the number, okay. For example, 2/3 times 3/2 would be 1. Okay, so the inverse of the multiplicative inverse of 2/3 is 3/2. Okay. Division is the opposite of multiplication. So when we're dividing two numbers, we can just add the multiplicative inverse of the second number and multiply. So a divided by b is the same as a times 1 over b. Okay. Now b can't be 0 there. So here's some properties of fractions. When we're multiplying fractions, we don't need a common denominator. We can just multiply the numerators, a times c, and multiply the denominators. So 2/3 times 5/7, we don't need to use 21 as a common denominator. We can just multiply these two. 2 times 5 is 10, 3 times 7 is 21, and there's our answer, right? Simplify your fraction if you have to. Okay. In this case, we don't, right? When you're dividing fractions, take the reciprocal of the second fraction and multiply. So flip the second guy and multiply. So a over b times d over c is the same as a over b divided by c over d. Okay. So 2/3 divided by 5/7 is the same as 2/3 times 7/5. And then we could do the same thing we did in property 1, just multiply and multiply. So 2 times 7 is 14 and 3 times 5 is 15. Okay. Now when we're adding fractions, here's where we have to get a common denominator. If it already has a common denominator, you're good. Just add the a and b and keep the c. Okay, so 2/5 plus 7/5 would be 2 plus 7/5 or 9/5. Leave your answer in improper fraction form. You don't need to write it as a mixed number. Okay. If we have different denominators when we're adding, we have to get a common denominator. So here our common denominator would be b times d. Okay. Or we could use the least common multiple of these two, whatever they might be. So now we have to multiply these two or find the least common multiple to get a common denominator. Okay. So 2/5 plus 3/7, our common denominator is 35. So we're going to multiply this times 7 and 7 to 2/5. Okay. And this times 5 and 5. So we get 2 times 7 over 35 plus 3 times 5 over 35, which gives us 29 over 35. Now we're going to add the 14 and the 15 to get that 29. Okay. So for different denominators. Okay. Property 5, if we have the same number in the numerator and denominator as a multiplier, we can divide those out. If you divide by c here, divide by c here, you're going to get a over b. Okay. So 2 times 5 over 3 times 5 is just 2/3. Okay. And then finally, if we have two fractions that are equal, now they have to be single fractions, we can cross multiply. So a times b, or a times d, excuse me, is b times c. Okay, so if we have 2/3 equals 6/9, we can write 2 times 9 equals 6 times 3. If one of those is a variable, then you can solve for a variable by cross multiplying when you have a single fraction equal to single fraction. Okay, the last thing we're going to talk about in the first part of section 1 is the real number line. Notice zeros in the middle there. We call that the origin. But notice our integers here, -1, -2, -3, etc., and 1, 2, 3, 4. And you'll see a bunch of numbers in between here. Some of them are fractions or they have decimals that stop. Those are rational numbers. Then you'll see numbers like minus square root of 2, which is an irrational number, or square root of 2, or square root of 3, square root of 5, pi. So what we're saying with the real number line is when you put all the rational numbers and irrational numbers together, it fills up that whole number line. Okay, and there are no gaps. So every dot on this number line refers to either a rational or an irrational number. Okay, and then every rational or irrational number refers to a single dot on that line. We call that a one-to-one correspondence. Okay, so at 0, we're right in between, right? If we go to the right, we're going in the positive direction and we're going bigger. Okay, if we go to the left, we're going in the negative direction and we're going smaller. Okay, so if something is bigger, it's going to be to the right, and something is smaller, it's going to be to the left. Okay, and then that point in the center is called the origin. Okay, so for inequalities, if we say A is less than B, then we can say A lies to the left of B on the number line. Okay, so less than means it's to the left on the number line. If we say, now we could say it the same way in this way, B is greater than A, that means the same thing. In fact, you can read inequalities backwards. So A is less than B means the same as B is greater than A if we read that backwards. Okay. Now that means B is going to be to the right of A. Okay, if B is greater than A. Okay. If we say greater than or equal to, that means we would include the fact that they could be the same. Okay. So let's look at just a couple of inequalities where we can say, okay, minus pi is less than minus 3 because you can see minus pi is to the left of minus 3 a little bit. Okay. Square root of 2 is less than 2 because square root of 2 is to the left of 2. Okay. 2 is less than or equal to 2. Now they're the same, right? But because we have the equal to there, that's okay. Okay. If we couldn't say 2 is less than 2, but we can say 2 is less than or equal to 2. And then here we could say 7.4 is less than 7.5, right? Okay, so that's the end of part 1 of section 1.1. We'll continue with sets and inequalities next time for part 2.